Hi guys, Dr. B here. This is topic 2.7, VSEPR theory and hybridization. So the objective is to be able to based on the relationship between Lewis diagrams, VSEPR theory, bond orders, and bond polarities, you're going to explain structural properties of molecules and explain electron properties of molecules. So we're going to look at a few key terms such as hybridization, sigma bonds and pi bonds, not that type of sigma. Whatever that even means, I don't even know anymore. So molecular structure, VSEPR model, valence shell electron pair repulsion theory, predicts the geometries of molecules and polyatomic ions. The shape is determined by the lone pairs or bonds on the central atom of a molecule, as these are areas of electron density or charge clouds, and that they will help minimize electron-to-electron repulsions by positioning themselves as far as possible. Lone pairs of electrons repel more than bonds and tend to compress the angle between bonding atoms. So how do you do this? You draw out the molecular geometry. You draw out the Lewis dot structure. Remember, hydrogens are always terminal. The least electronegative element is usually central. You count out the bonds and lone pairs around the central atom. Use the arrangement of lone pairs and bonds to determine the molecular geometry from the chart provided here. You must memorize these because they're not going to be given to you. If there is more than one central atom, we determine the geometric shape of each central atom individually, and you just kind of do the same stuff. So if you have looks like you have two central atoms, you can figure out what is the geometry on each. So the number of domains is whether it's a bond or a lone pair, doesn't matter. They just count as domains. The molecular geometry is what's determined by the number of lone pairs on it. So for your flashcard assignment, whenever you have it, you're going to put together, well, the instructions will be given, but you're going to be putting together the number of domains, whether it is 2 domains, 3 domains, 4 domains, and then you're going to, well, I'll give you instructions later, so it's fine. So if you have 2 domains, the electron geometry is linear and its hybridization is SP. We'll talk about that in a bit. So there's going to be 0 lone pairs. You have a molecular geometry of linear. Bond angle is 180. You have 3 domains. The electron geometry is always trigonal planar. Hybridization is sp2. So you'll notice the number of domains kind of equates to the sigma and pi, the sp part of the hybridization. So 3 domains. There's an S and then 2p, so that equals 3. If you have no lone pairs and they're all bonding domains, it's trigonal planar. That's the same as the electron geometry. 120 degrees. If it's 1 lone pair and then there's 2 bonding domains, that's bent. The bond angle is less than 120. So for the test, yes, you should be aware that there is more repulsion from a lone pair. That you kind of can see that just by looking at the numbers. But if you if you put 120, they'll still give it to you. So I wouldn't stress out too much about that. If there's 4 domains tetrahedral for the electron geometry, sp3 is a hybridization. The molecular geometry is tetrahedral. Bond angle is 109.5 degrees. Trigonal pyramidal is if you replace if you take 1, you put 1 lone pair instead. If you replace 2, it's bent. The bond angles are less than 109.5, but if you put 109.5, it should be fine. Oh, these are the crazy ones now. I'll let you look at that because that's a lot. So 5 domains trigonal bipyramidal, sp3d, octahedral, 6 domains, sp3d2. Sounds like Power Rangers SP. Anyway, so luckily for y'all, the hybridization you only need to know is for 2, 3, and 4. So sp, sp2, and sp3. These other 2 for 5 and 6 you don't have to memorize, but you have to know the other stuff. So if you have 5 bonding domains and they're all bonding, it's trigonal bipyramidal, and there are 2 bond angles to take into account. If you replace one lone pair, it's seesaw with 90 and 120 degrees. If you replace two bond pairs, it's T-shaped 90 degrees. And linear if you replace three bonding with lone pairs. 6 bonding domains, octahedral for the molecular geometry, 90 degrees. Luckily, looks like for 6 domains, it's all 90 degrees. Square pyramidal, that's 5 bonding, 1 lone pair. And square planar, so flat square, as you can kind of see there, it is 90 degrees, square planar. So bond hybridization. To explain molecular geometries, we must assume that the atomic orbitals mix to form hybrid orbitals. The shape of a hybrid orbital is a mix of the shapes of the original atomic orbitals, such as S, spherical, and P, dumbbell. The total number of atomic orbitals on an atom remains constant, so the number of hybrid orbitals equals the number of atomic orbitals that are mixed. For example, you have methane, 2s, and 2p orbitals of carbon mixed to form 4 sp hybrid orbitals. In general, the sum of the superscripts, equals the number of electron clouds around the central atom. So the carbon atom is in stage 4 has 4 electron clouds around it. Therefore, the sum of the superscripts in sp3 equals 4. So like I said, you only need to memorize the first three, sp, sp2, and sp3. So if I were you, I'd put those on my flashcards when you'll see the instructions later. Sigma and pi bonding, not that type of sigma. Overlapping orbitals form a single bond that are known as sigma bonds, which are very strong bonds. The double and triple bonds are formed from p orbitals and are called pi bonds. A double bond contains 1 sigma and 2 pi bonds. The presence of pi bonds means that the bonds are unable to rotate. This leads to something called geometric isomers. These are molecules that have the same number of atoms, are the same atoms, but have different arrangements and are not superimposable. So then this is kind of beyond the scope a little bit of AP Chem, but yeah. So you see here, it's not working, hold up. Okay, it's fine. So you saw before where it said cis and trans. So basically cis is on the same side, trans means it's across the other side. That's fine. Okay, so bond length. There you go. Bond length and strength energy. As the number of bonds between atoms increases, the bond increases in strength and energy, but decreases in length. Pi bonds, present in double and triple bonds, pull the atoms closer together. The triple bonds are the strongest and shortest with the highest energy, while single bonds are the longest and weakest and have the least amount of energy. Bond order. Bond order is the number of bonds between two atoms. When the bond order increases, the bond length decreases and the bond energy decreases. So these are kind of just elaborating on stuff you already know, but it's giving it a name. So you might want to keep these in mind. Single, double, triple bond order 1, 2, 3. For a molecule that exhibits resonance, we see that the bonds that have resonance are experimentally determined to be the same length. In ozone shown below, we would expect the single bond to be longer than the double bond, but that is not the case. They both have a bond length that is halfway between a single and double bond. So the bond order is halfway between a single and a double bond. Another way to think about it is that if there are 3 bonds that are shared between 2 atoms, so 1, 2, 3, 1, 2, 3, divide by 2, so 1.5 is the bond order. So in the next slide, I'll show you nitrate ion, which is NO3 1-. You will see that the 4 bonds on the nitrogen, there's the 4 bonds that are shared by the nitrogen with each of 3 oxygens. So the bond orders, so you have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 4 divided by 3 is 1.33. So this is what resonance is. This was in 2.6, which I flipped for whatever reason. So just kind of keep that in mind. Bond polarity. When electrons are shared in a covalent bond, the shared electrons spend more time around the more electronegative element in the bond, like we've talked about before. This gives a more electronegative element a partial negative charge, so the delta, a dipole, negative dipole, and the less electronegative one will be slightly positive, resulting in a polar molecule. The arrow in the diagram below points to the more electronegative atom and where the electrons tend to spend more time. HCl is a polar molecule because there's a dipole moment that isn't canceled out. If a molecule is polar, it has a dipole moment, which is this stuff right here. To know if a molecule is polar, though, you need to know if the bonds are polar and what is the overall shape. So, example, we have CO2. We know that it's linear. We've done it before. Drawing the arrows pointing to the more electronegative element in equal and opposite directions demonstrates the molecule is polar bonds, but it's overall non-polar because they're pulled in the opposite directions and they cancel each other out. Example B shows a water molecule. Because the molecular geometry is bent, drawing the arrows indicates that the dipoles do not cancel, therefore it is polar. Determine the molecular geometry and predict the bond angles of the following. So we have ICl2 minus. So we have 7 plus 2 times 7 plus 1 because of that minus charge. That's going to be 22 electrons. So for these, if I were y'all, I would try to do the Lewis dot structure version, like with the dots. So Cl. So we know that we can have a central atom. So the I is actually going to be in the middle. The Cl's are on the opposite sides. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to bond here. Oops. And this will bond here. So remember the dots are in clouds, so they kind of can swirl around the atom, the nucleus. So then technically you can have the lone pair that's right here can be somewhere else. And you should be aware that you probably need to put these lone pairs because you're going to help determine the molecular geometry and the bond angle. So we can see that it's, how many domains are here? There are 1, 2, 3, 4, 5. So 5 domains. 3 of them are lone pairs and 2 are bonding pairs. So this is going to be linear and 180 degrees. SOF2, so we have 6 plus 6 plus 28. It's going to be 40 electrons. So the one on the left tends to be the least electronegative element. So S will be in the middle. O is probably going to be on the outside somewhere. And then you have 4 Fs. So put an F here. This will probably triple bond here. And then we have, wait, hold on, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12. Of course. So 1, 2, 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. You put your F's around. So this electron here is the one I shared with over there to make the double bond with the O. So then this one technically does not exist because it's now over here on this side. 2, 2, 4, 6, 8, 10, 12. Okay. Well, that sucked, not gonna lie. So we have 6. How many domains? We have 5 domains, and they're all bonding domains. So this is the trigonal pyramidal. 90, 120. So this is a double bond. We have our 2 bonds up here, here, and here. And we have these as well. Draw the Lewis structure for the following chemical species. Indicate the hybridization on the central atom and the total number sigma and pi bonds. So we have a total of 10 electrons. Then we have a total of 12 electrons here in this one. So if this is carbon, let me do that. And then nitrogen. So there's going to be a triple bond here, then there's going to be an extra electron there at least. And because it's a because it's an polyatomic ion, or it's an ion, we have to make sure we account for this extra electron out here from the negative charge. So 2, 4, 6, 8, 9, 10 electrons here. So the hybridization is sp because it's a triple bond, so the sigma is 1, pi is 2. We have formaldehyde here. So there's 3 bonds, so sp2 is a hybridization. 3 sigmas, because 1, 2, 3, and then 1 pi because of this one right here. Is ammonia polar or nonpolar? Explain using molecular shape polar bonds and indicate if they cancel out. So we know that ammonia is like this. So ammonia is polar since the central atom has lone pairs. It is trigonal pyramidal. The NH bond is polar. And the molecule is asymmetrical. The polar bonds do not cancel out. Consider the Lewis structures for ethane and ethene alone, or below, sorry. It's a carbon-to-carbon bond in which molecule has the highest bond order. Which of the following has the lowest bond energy? So the lowest energy would mean probably single, so it's going to be the ethane, single bond. Therefore, ethene, between these two, has the highest bond order because there are more bonds involved. And there's one called ethene, yeah. That's going to be a triple bond, but don't worry about that one now. Draw the Lewis structures for ethane and carbon dioxide. Predict the molecular geometries. And the bond angles for each molecule. For ethyne, predict the geometry around each central atom. So we did these two, we've done these two already. So ethyne is this, carbon dioxide is this. So we see that on this first carbon, carbon 1, this is carbon 2, just for the naming of it, I guess. Carbon 1, it's going to be 180 degrees, and it's linear. Carbon 2 is also 180 degrees and linear. The carbon in CO2 is linear, and then 180 degrees as well. So we have to keep these in mind for for part B. So these are both linear and 180 degrees. So the question is asking, when the following reaction occurs, does the hybridization of the carbon atoms change? So this one is here and then here. So based on the previous answer, it's asking if hybridization changes. So we both know they both have two bonding domains, and they're both linear, so they are both sp hybridized. So the ethyne and CO2 are both sp hybridized. So the hybridization does not change. Oh, sorry. Last one. In the Lewis dot structure above, determine the hybridization of each carbon atom labeled 1, 2, 3, 4, and 5. What are the bond angles at A1, A2, A3? Sounds like a barbecue sauce. And determine the number of sigma and pi bonds. So carbon 1. You have 4 domains on it. So this is going to be sp3. Carbon 2. You have 3 domains, so it's going to be sp2. Carbon 3, where are you? You have 3 domains, so it's sp2. Carbon 4, you have 2 domains, so it's just sp. And then carbon 5 is also sp, because there's only 2 domains. Find the bond angles at A1, A2, A3. So we can see there are 4 domains, and they're all bonding domains at A1. So the angle is going to be 101.95 degrees. Letter A2, 3 domains, they're all bonding domains, so the bond angle is going to be 120. And then A3, it's 2 domains, linear, so it's going to be 180 degrees. Whew. The total number of sigma and pi bonds in the molecule. So sigma bonds, and then pi bonds. So you have to, let's see if I can do this one. Change the color. So we're going to count out our sigma bonds. So that every bond, so if between 2 atoms, if you have a single bond, that counts as a sigma bond. But if you have other ones that you add, like double or triple, those are going to be considered the pi bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds. And then for the pi bonds, you just count the rest. So you have a double bond here, so I counted for that one. And then I have 2 more from the triple bond. That means there are a total of 3 pi bonds. Whew, that was a long lecture. All right, gentlemen, if you have any questions, please let me know. Hit the like, subscribe. Thank you. Thanks. Bye.